Hi Advanced Hire. So this is lesson 2 of the statistics unit. Having done some work looking at types of data, nominal, ordinal, interval and ratio, now we need to do some work on exactly how we would collect this data. Don't become confused at this stage. We're not talking about fieldwork techniques here, we'll do that separately. I'm simply trying to get to grips with how we will make sure that the data we collect is of a large enough sample size, and how we make sure that that sample is collected in a way that is not biased. So we need to look at what sampling is and then how we use different sampling techniques. The first thing to look at is that there are 3 types of standard sampling technique that we will deal with: random, systematic and stratified. At times you will use some or all of these techniques. Sometimes you might use them all at the same time, and sometimes you'll use them selectively. It's your job to understand these terms well enough to know when to apply them appropriately. That will be relevant in your study, your project, but also this will be relevant to exam questions. So, what is sampling? Well, a sampling strategy is one of the most important things you need to think of before you go out into the field and collect your data. You need to think about how are you going to lay out your fieldwork. Imagine going to a beach and you're going to try and investigate the variation of vegetation over that beach from the embryo dune to the climax vegetation. You will need to design a method by which you can collect that data. You need to make sure that you do it in a way that is unbiased, so you're not choosing particularly good places to collect your information. You need to do it in a way that is repeatable, that is reliable, that is robust, and also that is safe. Sampling strategies allow you to achieve all of these outcomes. It's one of the first things that any examiner will look for in your methodology for your study. So, random sampling first. This is where each item from a population that we're counting, remember the word population simply means the thing that we are counting. It doesn't mean people. It could be a population of insects, a population of plants, a population of pebbles that we've counted. This is where each item from a population has an equal chance of being selected. And this bit about equal chance of being selected is really important. If every pebble you're pulling from a stream has a genuinely equal chance of being selected, then your sampling strategy has achieved randomness. And that means that it's not biased. And if you can truly say that your data is not biased, then you've removed the human element from its collection, or the human error from its collection, and your data is therefore robust and reliable. There's lots of ways that we would make sure that we are not being biased, and some of those fall into the actual fieldwork techniques themselves, which we'll deal with separately. But this is why random sampling is something you must always try to consider in planning any fieldwork. Typically, what would happen is that each population member, each member of the population, that means each pebble, or each plant, or each tree, or each whatever it is you're counting, would be assigned a number using a random number table. Random number tables are a resource which I'll show you in class. They're very straightforward. You can get them as an app on your phone, and it produces a random number between two values. That then allows you to randomly choose which sample you're going to take. I think it's useful to think about this in a more practical way. Let's imagine you are standing in a river and you need to remove bias from the pebbles that you are selecting. You would use a random number generator to randomly generate the number of centimeters you are going to dip your hand into the water away from the point you're standing at. And at that number of centimeters from where you are standing, you are going to pluck a pebble out of the stream. That makes the selection of pebble randomized and therefore not biased. And using a random number generator is a really important tool to doing that. It's important to note that you can use random number generators in lots of clever ways. For example, if you wanted to do a transect line, many of you will, and you want to do a transect line over a beach, just say, for example, it would be important to you that that transect line is also not a biased choice. So to remove bias from where to place your transect line, you could use a random number generator to select some grid references, and those grid references would then become the beginning and end points of your transect lines, and therefore your transect lines would be randomly chosen. You can use them to choose a direction that you're going to face. So for example, if you're doing an urban study, a random number generator could tell you which degrees on the compass you're going to face when taking a photo, or when measuring the noise level, or when judging the quality of the built environment. And again, that removes bias from those decisions. If you are taking a certain number of paces away from a transect line that you have drawn to sample the vegetation percentage, you would use a random number generator to determine the number of paces you will take away from your transect line to measure the vegetation percentage. So random sampling is quite straightforward, really. Its theoretical basis is that we want to remove bias. Its practical application is that you use a random number generator, which, as I say, you can download as an app to your phone for free. There's loads of them. Or you can even use a paper one where you just randomly stab a number on the paper. And it can be used in lots of clever ways. Once you get your imagination around the concept of random sampling, you can use random sampling at lots of different places in your study, and at every time that you do introduce random sampling, know that you will be reducing the bias in your study, and that's always going to increase the robustness of your results and the reliability of your conclusions. That brings us to systematic sampling. Now, this is where samples are selected in a regular manner. What regular in this context means is, for example, taking vegetation samples every 10 meters. Sometimes you might be working, you might not be working along a transect line, a linear sample, but you might be working in an area. Now, it makes sense, of course, to make a grid if you're doing an area, and you might sample at a series of points within that grid. This is called point sampling. But the point is that it is done in a regular manner, sampling every 10 meters, sampling every 5 meters, however far apart the points are on the transect line or in the grid. You could even use systematic sampling to sample passers-by, customers, in a shop, or even transport on a road. Selecting every 10th customer at a supermarket, for example, would be a systematic approach. It would also contribute towards the removal of bias. So systematic sampling is when you apply a regularity to the samples that you are taking. That's very important because it means that you are applying a set of rules to how you're collecting the data. You're applying a system to your data. It is systematic, and that will make your data more robust, more reliable, and more repeatable, because you now have this systematic structure by which you are sampling your data. In this image, you can see the two examples of what I was just describing there. Here we are at a beach. Here's the sand, there's the sea. And these, just imagine, are the dunes progressing towards the climax vegetation where you see the trees. You could draw a transect line. Maybe we would have used random sampling to select exactly where this transect line begins along the beach to avoid bias. Then we've used systematic sampling to lay the transect line out as we progress from the embryo dune to the climax. By doing every 10 meters, we are making it systematic, and this means that we know exactly where to stop to collect our data. And that adds to the strength of our study not being biased. We haven't stopped where we think the data looks good, we've stopped where our system tells us to stop. Here's a grid sampling, and it's just a more elaborate version of the same thing. And you can see that we have systematically divided a study area up into 10-meter grids, and we can sample sites systematically within this, always knowing that we are 10 meters from the last sample site that we took. Okay. Finally, stratified sampling. Stratified sampling is a little bit has a little bit more to it. It's not more complex, but it has a little bit more to it. Let's just deal with the word stratify first of all. To put something into strata means to put it into layers. So in this sampling strategy, we're obviously going to be breaking something up. And I find that a useful starting point. You're going to be using some kind of you're going to be trying to separate things in your mind when you're stratifying. So the first type of stratified sampling can take into account the relative proportion of different groups within a sample. Now, let's think about that carefully. For example, in a sand dune investigation, 2/3 of the dunes may be managed. That means that they are in a protected area of land, and they are looked after by a ranger or some kind of environmental group. And the rest of the dunes, the 1/3, are unmanaged. They're just wild. Anybody can walk their dogs on them. Anybody can walk across them. They are not protected. So if 9 transects are selected, then the correct balance should be 6 managed and 3 unmanaged. If 2/3 of the beach is managed, then you should make sure that your study includes 6 transects in the managed area and 3 transects in the unmanaged area. Reading through that example makes it quite straightforward, and opportunities for stratification in this way with proportion will become clear to you normally during the design of your study. Some examples might include, if you're doing an urban study, comparing different postcodes of a city, say, or different areas of a city, and the areas are different sizes. Well, you're going to have to account for that in the sampling If one area is, just if I was to exaggerate the numbers to make it easy to imagine, if one area is 100 miles squared and one area is 1 mile squared, is it fair to sample the 1 mile squared area 10 times and the 100 mile square area 10 times? Is that going to give you a representative sample size? The answer is, of course, no. And so you would need some way to be proportional. Now, because the example I've given, one is 100 times bigger than the other, it's obvious how you would do that. You would increase the sample size for one of them by 100. Okay. Stratification can also be used to filter out areas that are less relevant. The easiest example for this is on a transect line. And you might want to ignore certain areas. So if your transect line, when you go to the beach, has a play park somewhere on it, because you have randomly chosen where your transects go, and the transect that you chose with a random number generator happens to cut through a little bit of a play park, well, you would stratify that out. That means you would ignore it, because it's going to bias all of your results. You're going to have a big area there that has no sand, no seashells, no plants, whatever it is that you're counting. So you would stratify it out. And then you could take account of the fact that that transect is perhaps a little bit shorter, and then you could use proportional stratification to account for that with the number of sample sites on that transect. Stratification can also be used to ignore areas that don't form part of the study. So water hazards and other dangers are the thing here. So stratification has a number of different applications, and it's something to use to discuss with me, with your teachers when you come to use it. And very broadly, once again, it is the most common use for it really is for filtering out areas that are less useful or relevant, or to filter out areas that are perhaps dangerous. So in summary, we have three types of sampling. Random sampling removes bias from our study. Systematic sampling provides rigor to our study. It allows us to be regular and to be systematic and to have a system that we apply to the collection of data. And stratification allows us to target areas, or rather ignore areas that are completely irrelevant, and to focus the data collection on the areas that are relevant. And also, where two different transects or study areas have markedly different populations, it allows us to approach those populations in a proportional way, so the data we're gathering is fair and representative. Okay, that's sampling.